Hello everyone, as promised, we are beginning a new unit today in multivariable calculus. Today we are going to be talking about volume and multivariable integrals. We'll really be talking about 2 variable integrals and 3 variable integrals. But it should be noted that everything that we talk about is going to be expandable to pretty much however many dimensions you like. It's just 2 and 3 dimensions is easiest. The other thing I would want to say is that multivariable integration is really the combination of 3 topics in math, and that is calculus. Obviously, you need to know how to differentiate and integrate, algebra, and coordinate geometry. Now, coordinate geometry is something we didn't really discuss in single variable calculus when we were dealing with integrals, but we will be dealing with it in multivariable calculus because the regions that we will need to integrate under are typically defined by different shapes and things of the like in multidimensional space. Now, what do I mean when I say volume? So we really should cover that before we get started with double integrals. So let's go over the definition of what we're talking about. So let's define the Cartesian product. The Cartesian product is essentially the definition of a rectangle. So this means these are our x bounds of the rectangle and these are our y bounds of the rectangle. So if I'm going from A to B, so let's draw out a 3-dimensional coordinate space. So there's our 3-dimensional coordinate space. I have a rectangle, and on the x-axis, I'm bounded between A and B. So here's A, and here's B. And then on the y-axis, I'm bounded by C and D. C and D. So that's our Cartesian product. Now we can draw out a rectangle if we define each of our points here, right? So there's each of the points. And I can draw out a rectangle. And then we call that the region R. We call that region R. And then above region R is going to be a function. So above it is going to be a function of some sort. This function can be kind of wavy. It can look however we want it to. There's our function, right? And there's another bit of our function up here. Maybe it goes like that, and then it goes like that, and then it goes like that. And that is our function that's our function surface over the region R. And now, what I'd want to do with a double integral, with multiple integrals, I'd want to integrate over A and B and C and D, and what that gives me is the volume under a surface. So it's a really nice analog to the area under a curve. And unfortunately for 3-dimensional integrals, 3D integrals, or triple integrals, we really don't have that luxury. It's a little bit harder to visualize, but the volume analog is very nice. Anyways, what we will now do is we will take the region R, so we'll draw it as a 2-dimensional rectangle now, and we will divide region R into tons of little squares. And this could be here x sub 1, x sub 2, all the way over to x sub n. Then here we'd have y sub 1, y sub 2, and then we go all the way up to like y sub m or something like that. So we define one of the little rectangles, Rij, as being the Cartesian product of x sub I minus 1 with x sub I with y sub j minus 1 with y sub j. Okay, so now what we want to do is we want to sum all of these up and find the volume of one of these rectangles. So if I have my surface, so if I have a little rectangle, this is r sub ij here, and then that is underneath some little bit of surface, right? That's beneath some little bit of surface here. I want to find the volume in here underneath the surface. Then what I do is I just multiply the height. This is the height, and the height is going to be f of x sub ij, comma y sub ij, times the little change in area, which we have down here, which is delta A, so as we discussed earlier. So now if I want to find the volume under the whole region, if I want to find the volume under the whole thing in there, then I'm going to need to sum, and that's going to be an approximation. So the approximation is going to be from the sum from I equals 1 to m, and then the sum again from j equals 1 to n of f of x sub I j, y sub I j, times the change in area. So what we have is we have tons of little rectangular prisms being multiplied by one, or being summed over based on what our bounds are, right? So if I want to find the exact volume, then I take the limit as m and n both approach infinity, the sum from I equals 1 to n, or m, and then the sum from j equals 1 to n of f of x sub I j, y sub I j delta a. And we call this the double integral. So if you remember, if I had the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I delta x, then that was equal to the single integral between a and b of f of x dx. Well, now we're doing a similar definition such that the volume is equal to the double integral over the region of f of xy dA. Now notice the notation here. When I do a double integral, I do two single integral signs, and then I put r on the bottom. And r is any region. R is just a region that we will define later. It's just more compact that way. We'll define the region later, and as you note, there are no bounds on any of the single integral signs. And that's something that we'll cover later when we deal with iterated integrals. But then we obviously write our function f of xy, and then we have our differential area. Now, the differential area doesn't mean much to us right now, because I don't really know what that means. It could be anything at this point. So our definition of the double integral is quite abstract right now. And in fact, this formula here, we covered back in, I don't know, Unit 4 of single variable calculus, how hard it was to find exact areas under curves by using the definition of the integral. And we needed the fundamental theorem of calculus to help us out with that one. With the double integral, it's even harder to do that. So we are going to develop tools, and one of them is the iterated integral, which we'll learn later in this unit, and that will help us out. But for now, all we've got is this. However, what we can do is we can approximate it very well, and this here is called the double Riemann sum. So we have the double Riemann sum that we can use. So it's a great method of approximations because this is a very easy way to approximate. So let's try an example with the double Riemann sum. So let's approximate the volume under z equals negative x squared minus 2y squared plus 16 under the Cartesian product of 0, 2 times 0, 2. So what we have here is we have a region in here in the space, and we have the region going between 0 and 2, and then 0 and 2. So that's our region. And we want to find the volume under the curve negative x squared minus 2y squared plus 16 under that region. So what we're going to do is we're going to divide the region into 4 equal squares. So we divide it into 4 equal squares here, and we use the upper right corner. So we want to use the upper right corner of this, so we're going to get a maximum, right? So what we get is we get that the delta area is equal to 1 because we have 1 here and 1 here. 1 times 1 is 1. So that makes our volume pretty nice. We get the sum from I equals 1 to m, then the sum from j equals 1 to n, f of x ij, y ij, and then delta a just disappears because that's going to be 1. So what we get is we get f of 1, 1 plus f of 1, 2 plus f of 2, 1 plus f of 2, 2. Then all we need to do is plug in for z and then find those values. And then we get 13 plus 7 plus 10 plus 4, which is, of course, 34. So thanks for watching today's video on the introduction to double integrals and volume. So in the next video, what we're going to do is we're going to look at the midpoint rule, and then we are going to introduce the iterated integral and partial integration. Partial integration is going to be a very important topic for not only this unit, but also vector calculus in the next video, or in the next unit. So thanks for watching. We'll see you next time. Bye.